everybody, my name is Stefan Ringbeck from Trina Solar. Today we have a webinar about PV self-consumption challenges and opportunities. The webinar will take approximately 20 to 30 minutes. If you have questions, please put it in the chat or in the question field, and then after I went through the complete presentation, I will answer the questions. Anyhow, if you have questions, then you can also write me an email. My email address is stefan.ringbeck@trinasolar.com, and enjoy the webinar. Today we have following content. First, I will give you a brief introduction about self-consumption. What does it mean? What are, for example, local differences? Then we go to the local differences. There I will went through 4 different locations to give you a better understanding what does it mean to have self-consumption, and especially what are, for example, regional differences. Then we will go to load profiles and energy harvest, and at last point we have the levelized cost of energy, the LCOE, and a few information about payback time and examples. First, with introduction. As you can see here on the left hand side, here you have a graph about energy production, the daily one. It's in the marked here, so it's going more like upwards, and then from left to right you see the yearly behavior of the sun irradiation and as well as the production. That means based on this production you see that it's highly flexible and it's not constant, and if you want to have an highest rate of self-consumption, and especially on the application where you are, for example, on residential or on commercial or utility, this energy profile, which is driven by the sun and your needs, should be best aligned to have the best self-consumption rate, so that most of the energy you produce by your PV panel gets directly consumed in your building or facilities instead of fitting into the grid to have the best payback time. On the right side you see a small picture about what does mean the PV and with self-consumption. So here we have the PV modules. They are collecting the energy from the sun. Then you're going to the inverter or inverter combined with a DC storage system, and then you have a management unit. What is the setting? Okay, I will go to the grid or to another storage system or directly consuming in the house, and for sure the energy what doesn't get used or doesn't get stored will be then fed into the grid. This is a small introduction about what's possible, and now we want to go into local differences. So first of all, today we want to show, because we have here a very global approach, so we want to go to Stockholm, Marrakesh, Johannesburg and Kalmar to see what happened at the different location, and also how the different location behave compared to other one, and what does it mean for example, for the system design, or for example for product selection, so that you can offer your customers the best solution for their needs. First of all, I want to give you a little bit an in-view in the sun position, because the sun position, as we know, is extremely different from location to location. Here on the south hemisphere I have here for example Kalmar in Chile or Johannesburg in South Africa, and you already can see here that, for example, the sun height in Kalmar at the minimum is approximately 44 degrees, and for sure it reached, because it's close to the equator, it reached the 90 degrees, so that means we have direct sun 90 degrees to the ground. And Johannesburg is way more south, but still you can see that even if it's very south, you see that we still have a quite high sun height during winter time, and then in summer we are reaching close to the 90%, so it's approximately 85, and this leads also to a different behavior in the energy collection, and this can be also considered in the system design, so that you can offer for your customer and the needs. That means, because it's always depending on the energy profile, what I will discuss later, to see what is the best option and what are the different options, and what are the differences between. Then For the north hemisphere, we have Marrakesh. It still has a quite high sun high compared to Stockholm, which is very north, and we see here that the minimum sun high is about 7 degrees and the maximum reach close to 55. Later we'll see what does it mean for the energy collection, and we also will go through examples, what for example the module rotation, what are the differences. Here that's a printout from PVSys showing when the energy get harvested. That means it's a hourly plot. So here I always have two examples. I have an example here in blue. It's always single orientation to north if you're in the south hemisphere, or to south if you're in the north hemisphere, and then an east-west system. For sure, track system can be also taken into consideration, but here I want to show clearly the differences between two different orientation. As you can see here, for example, in Kalama, with east-west orientation during the summer months, you see their small benefits, because you have the direct sun from top. That means the misalignment and the low angle from the module doesn't count. But compared to the winter time, here you can see that the east-west system has a much higher drop than here the north-orientated system. In Johannesburg, we have a similar behavior. So in the summer we are slightly better with an east-west orientation, and then during winter for sure the north system will be the better solution. That means depending on what are the needs from your customers. So for example, your customer has a commercial building with a high demand of air conditioning needs, then because air conditioning is usually only needed or mostly needed during the summertime, then the east-west can be the better one, because you have slightly benefits in the during the summer months. You also have the capabilities to have higher capacities on the roof or on the ground close to the facilities. And then during winter time you have a lower energy harvest, but you also have a lower energy demand, because energy what is consumed by the air condition is reduced due to colder temperatures. That means you can, with the system design, you can somehow adjust the system design to your local, or to your first to your local energy profile, and to your profile from the facility, for example for the commercial building. Then if you take now a look to Marrakesh, here you can already see that during summer there's more like no difference between south-orientated system and an east-west system, and then during winter you see there is clear benefits from an east-west. That means in Marrakesh, for example, if you're on highest energy yield, it's better, more for example, go with a tract or than with a south-oriented system instead of an east-west system. Only if you say, okay, I have limited land or limited space, then it's better to go with an east-west to have the maximum capacity on the given area. If you now take a look to Stockholm, here in Stockholm you can see that east-west is really difficult, because the differences between the south-orientated system and the east-west system is fairly big. That means although that the energy harvest for an east-west system is low, and as at least the levelized cost of energy will increase dramatically. And also in terms of improving the capacity, there's the question, okay, does it make really sense, or is it only to more like equalize the differences between the south-orientated and the east-west system? As you could see here, depending on the location, you see that the module orientation or the system design it will impact the energy harvest and will bring different advantages to your system and then to your given project. So in terms of self-consumption, you always need to know, okay, what are the needs of your customer, what is the energy profile, what is local production, and then you can align and then you can optimize the system. On the next slide, I want to show what are the different energy productions. Here I displayed the energy injected into the grid for different orientations. Basically it's a comparison between south and east-west, and then the dotted line Here is the best one is, for example, in Calamar is the tract system, and you can see that, for example, in winter, although the east-west system, the tract system is on a similar level like a south-orientated system. But for sure, in the summer, when you have the highest irradiation, then it's fairly better because you have a wider curve. That means you harvest more energy per day. Here in Marrakesh, you can see that clearly during summer you have the best one, and then in the winter you also can be slightly, let's say, slightly better, slightly worse than south-orientated system. The difference here is because I used a one single axis tract system, and the axis is going from south to north. That means the tracking will happen from east to west. That means there is no tilt angle of the modules to the sun. That means with a more direct sunbeam, you have better energy production, like for example in extreme south position or north, like in let's say Stockholm or Marrakesh, because then you have more you have not optimized angle, and that means you have a reduced efficiency. Next, I want to show you some hourly curves. The curves are comparing, as well as on the last slides, the two solutions, south-orientated and east-west. So if we go now for summer, for example, here on the northern hemisphere, we have here Marrakesh, and then we have here the curve. We have here compared the system what is orientated to south and then tilt angle of 20 degrees compared to an east-west system with a tilt angle of 10 degrees per each side. As you can see, with the east-west system, you have a more wide curve, and the peak during the noon is only slightly below the south-orientated system. Because we didn't reach the 90 degrees, so there's still a slightly impact, and with the south-orientated, you're slightly better orientated to sun. So the angle of incidence is better. If you go now to Stockholm, there you can clearly see that, okay, if during the morning I have more energy production, and then during lunchtime, as during noon, it's a big difference compared to the south-orientated system, and the same in the evening. So the curve is wider but lower. That means if you, for example, a private home where all people are working, that means you need energy in the morning, you need energy in the evening. During the day, everybody's in work, so the energy consumption or the energy demand of the building will be fairly low. That means even with an east-west system, even knowing, okay, it's not maybe the best solution in terms of highest energy yield, but it fits better to my profile because I usually need the energy during evening or morning. Then maybe it's better to install in east-west because the curve is wider and the energy will be produced at a time where you need it. That means also the requirements, for example, for storage or for storing the energy will be slightly lower. That means you can also have, for example, smaller batteries, or you have an earlier power harvest in the battery. If you now go to the southern hemisphere, if you're now comparing Kamala and Johannesburg, we even here north-orientated compared to an east-west system, then you can see here that the blue curve, the north curve, is during the summer lower than the east-west. The same here in Johannesburg. In Johannesburg, it's a little bit more extreme. And even the curve is wider. That means, especially during summer, if you have, as already mentioned, a high demand, for example, for air conditioning, then the east-west could be a very good option in this region because you have a much better energy harvest, and then you can directly use energy. If you now take a look on the winter period, though here we are close to midwinter, first, I want to compare the northern hemisphere. I'm starting with Marrakesh. In Marrakesh, you can see that the east-west system has, for sure, it has a disadvantage, so the south system has an advantage. But if you, for example, use energy for air conditioning, then it's maybe fine, because if you self-consumes your energy, then you reduce it from your bill. But if you need to fit in, and if you may need to fit in too much, that means you only get a small money back, and then it's better to have a proper size system and really a system what is producing the energy. Or if you need heating system, for example, because you have a special application what needs more heating than in the winter, then it's better to go with an south oriented, because then you have the production during the year when you really need it. If we go now to Stockholm, then you see here the big difference between the east-west and south-oriented. You can see that the east-west, due to the extremely low sun angle of close to 70 degrees, that means you have a big impact of the angle of incidence. That means the irradiation beam is coming to the module on an extremely flat angle. That means the efficiency of the module is low due to the angle of incidence. That means that during the winter the east-west has more like now power, and only a south-orientated system will produce energy what can be used in your facilities. If you compare now this with the southern hemisphere, then you can see that there's still a difference. The difference is, for example, lower than in Stockholm, but also you can see, for example, Kalmar, which is much more close to the equator. That's the difference between the east-west, and the north-oriented system is smaller than in Johannesburg, which is more far away from the equator. And you also can see that from the curve, it's also smaller. So it's not only the peak is not only lower, even the curve width is smaller, which is for sure which means for sure that you harvest less energy. Now I want to go to the load profiles and energy harvest. Here I have placed examples. What does it mean to have a different tilt angle for the modules? What does it mean for the capacity? Capacity means how much kilowatt or how much modules you can install, in this case per hectare. I have here basically two curves. The blue one is always within module having an efficiency of 16%, and then the orange one are modules with an efficiency of 17.7%. Though, for example, the mono products we are offering. And then you have here the different behavior, because even, for example, 90 degrees in an east-west, for example, can be used as a facade example. The same for south-oriented, if you make it 90 degrees, for example, on a balcony, at the fencing, or even on the facade. And you can see that the behavior is different. And even if you're comparing both, so for example, here's the south and an east-west, then you have here even the break-even point, so until which point it makes sense to you the other, or the one solution or the other solution, even in terms on how many modules you can place per hectare. This is here displayed for Kalmar, as well as for Johannesburg, for Marrakesh, and for Stockholm. And you can see that the behavior, for example, between Kalmar, Johannesburg, and Marrakesh is quite similar. And Stockholm, due to the extreme position, is fairly different, especially for the south-orientated system, because the south-orientated system is needs to be set in a very high module tilt angle, which means that you need a big distance between the first and, for example, the next row on a commercial building. I mean, if you're on a residential roof where you have one surface and it's no difference, but if you have a utility scale project where you have more rows, or a commercial one, then you also need to know, okay, how much capacity can I place? And due to the high module tilt angle, what I need in the very north position to have a high energy harvest, you have a very low capacity. And even this can be taken into account in the system design to play with okay, energy harvest versus capacity, and what is the best solution. If you go now, for example, to our load case profile, so the load case profile here, basically the gray curve, what I currently mark with the mouse, is estimated energy curve, for example, for if you have bigger house with several apartments where the people are during the day they are on work, only a few people coming back, for example, for lunch, time to make lunch, and then for sure you have a peak load in the morning where everybody's standing up, preparing breakfast, making ready for work, then during lunch or after, then during lunchtime preparing the lunch, and for sure then in the evening with lighting, entertainment, all you need for the life. And if you now have the PV curve, here although the example with the north-orientated system, because here in this example it's placed in Johannesburg, so it's in the southern hemisphere, and in east-west systems you see there during the midwinter the different productions. Though we have here the orange curve for the east-west and the blue one for the north, and you can see that especially during the day that your production is higher than what you currently consume. That means everything what is below the zero curve, that means here this part, or then for the blue case the bigger part, can be, for example, sold to the grid at a certain price, or then stored to a battery, for example, then using the stored energy in the evening when you, for example, having your entertainment system running, the light, preparing the dinner and stuff like that. If you now compare, here I compare the same energy profile, so I said, okay, I have a load example for all locations to see a little bit or to show a little bit the regional or location, the local behavior. So the load curve is for all cases the same, and then we have here the energy harvest curve. So as always, the blue one for the single orientation and the orange one for the east-west for the two orientation, and then you can see here slightly differences when the energy will be produced for sure, and then what does it mean for your, for example, for your consumption from the grid, where you can see here with the dotted lines when the consumption from the grid will be reduced, and when you have an overcapacity of energy, that means that you are able to store or sell energy. And you also can see that, for example, the peak during lunchtime, what is always at the same time, slightly shifted, and even from the depths it's different. And you also can see that the east-west orientation, depending on the location, have different advantages and at which time you really need the energy. Or for example, here in Stockholm you see, okay, during morning my energy consumption from the grid is with an east-west lower than with the south orientated, but then during lunchtime, okay, I don't feed so much energy back. But maybe this, depending on if you have storage system or if you can sell it to the grid, it makes sense to fit it into the grid, or maybe have another solution. For sure, if you have a different curve, for example, if you know make example here with air conditioning, that you have here more the peak, that means, okay, then you have here a small amount of what you can store or sell. Now at one of the last points, I will go to the levelized cost of energy and payback time. So I will use the same examples to show different behaviors, how the levelized cost of energy, the system costs behave. And as last point, I will give a short example about payback time and what does it mean. First of all, as we know, the levelized cost of energy can be broken down in several cost points. That means we have here the BOS costs in a fixed part, for example, like the inverter, or the variable part like substructure or cabling, then the module. Then one big point is the financing. For example, especially for bigger projects, we need a partner to finance. And then the OPEX. OPEX are operation and maintenance costs, operational costs, and then you have that for development, for example, project development costs, especially for then utility scale projects. Besides, here it's only displayed the cost figures and how the cost figures are split. Additionally to the cost figures, you always have the energy. That means the amount of energy you harvest by your system. and for sure it's impacted by the modules you're using, by the performance of the modules, and even, for example, how operation maintenance can impact the system. First of all, why is it important? As you could see in the page before, roughly 1/3 of the levelized cost of energy cost is driven by financing. As you could see here, Trina is the most bankable module manufacturer in the world. That means it's the easiest one to finance, which means with the easier finance and may even cheaper finance, it will deliver you an advantage at your levelized cost of energy, because you can have the money cheaper. Money cheaper means you have lower total costs, which is a clear benefit, which means this increases your return of invest and the profit. The second point I mentioned is also the energy harvest. Energy harvest is one of the important points, because it's always the energy, and if you can collect more, it's better. As you can see here, it's a graph from a project in Italy, what was installed in 2011. And you can see that our modules here are offering better performance than expected. So the performance ratio is, as you can see here, approximately 3% higher than guaranteed. That means that your return of invest is better, and as well as the profit. Another point is, for example, the warranty. If you're now here we are comparing different kind of models. So, for example, our friend modules versus the DuoMax module. The DuoMax module is a glass module, frameless design, which has an improved PID reliability and total reliability. So the PID effect is further reduced to standard modules. And for sure we are offering, due to the advantages of the glass design, we are offering a smaller annual degradation of only 0.5% instead of 0.7%. That means over the project lifetime, in this example here, for example, an example in South Africa, then we have a system cost of approximately 16.5 rands. The 16.5 rands is approximately €1 or $1.1 per watt. The DuoMax has additionally the advantage of having the 1500 volt capabilities. If you take now all the advantage into account, that means the reduced degradation, the increased system voltage. That means in terms of levelized cost of energy, using in a utility scale project, for example, the DuoMax can reduce the LCOE approximately 8% due to the advantages in terms of degradation and the higher system voltage. First, I want to show you some sensitivities. So if you have, for example, a benchmark or a default LCOE of approximately $6 per kilowatt hour, and for example, in terms of quality, so if you're using extreme cheap module, then you might have an increased exchange rate because you have more defective modules. That means if you're only looking for the price on the modules instead of also looking for the quality, you might have an increased exchange rate, which is impacting your for sure your levelized cost of energy. And if you spend and invest into quality products, then you also can reduce it because you have a lower exchange rate, like in the average. And the energy yield. Energy yield, for example, like showed in the graph before in our Italian system, where we are better than what is guaranteed. That means the LCOE get reduced like calculated or simulated. If you have a product what doesn't perform well, then you also have an impact on the negative side. That means you increase your levelized cost of energy and the return of invest will go down, and for sure also the yearly degradation, because this can be also, it's the same like an energy yield, because it's a loss of energy harvesting per year. It's more like an aging, let's say it's an aging effect or several aging effects. So with yearly degradation, if you have a reduced yearly degradation, like shown before, from a reduction from 0.7 down to 0.5, this has a quite big impact. Though it's important that you take a look on, especially for utility, on the yearly degradation to ensure that you have low and lowest levelized cost of energy. That makes always sense if you have project. It takes a look on what are the different opportunities, for example high efficiency because you have a lack of space, or for example with the dual max because you're in a critical location, so that you need to take PID as effect into account. It's always good to spend money in good quality to ensure that you're on a good levelized cost of energy level. I also want to show some impact on the operation maintenance. Here, this is an example showing the soiling losses. Soiling losses is, for example, if you're in an industry region and if you think about, okay, what can I do for maintenance, for example, module cleaning and stuff like this. Here it's shown that the impact, and you can easily see that the monthly soiling and the soiling increase can be quite big. So you can easily lose 10-15% depending on the location. If you're, example, for in desert regions with a lot of dust or close to an industrial or agriculture, we have, for example, if you're in the industrial, like from the like fume gases, what is then a small dust stick to the module, and especially if you then have no frequent rain, what is partially removed, then you need to clean the modules. And based on the location, this needs to be optimized. For example, in the desert region where you have a lot of dust with sand, what is sticky, it sticks on the module, can go quite fast and you lose a lot of energy. And if you lose the energy because the modules are covered by sand and dust, that means it's an increase because the modules will not produce at the best point because they're covered with dust, and then you need to maintain, and this can be also optimized, and it depends also on the system design, how easy the system will clean itself, or how easy this is for the people or machines to clean the system, to have it in well conditions to have a good running and well running system to achieve the lowest levelized cost of energy. Here I also want to show the levelized cost of energy, the LCOE, depending on the module orientation. I took the same examples like before, so I will compare here Kalama, here in utility, Johannesburg will be commercial, Marrakesh utility scale. So utility scale usually ground mounted and commercial usually rooftop mounted, for example on an industrial hall or on bigger commercial buildings where you have a lot of roofs, so flat roofs. And you can see here in all the graphs it's quite similar. So you have here the system costs as a blue curve, and then the levelized cost of energy as orange one. And we always go here from 5 degrees up to 90 degrees in the east-west, and the same here we have the tract system. For sure the tract system in Kalama, due to the location with extremely high irradiation, tract system will collect the most of the energy. But tract system means also higher operation maintenance because you have moving parts which needs to be checked frequently, and if you have their malfunctions, then maybe the losses can be quite fast, quite big. So if you're on a remote location, it also makes sense to think about, okay, what is the best solution? Should I maybe go with maybe a slightly as a fixed system, like in south orientated on east-west, or should I really go with a tract? That's more like the risk assessment. So how high is my risk to have failure on the tract system? For example, the modules will stuck in the evening position, so they don't move back, and then you will lose 1, 2 or several days until your maintenance team is going on site to fix the tracker. With the fixed orientated system, you don't have the highest energy harvest, but you don't have moving parts. So from the operation maintenance point, the fixed one are slightly better, but in terms of energy harvest, they have disadvantages. And you can see the behavior. I mean, it's basically always the same, though, with the tract one, for example, the best one. And then for sure on 90 degrees, the modules are vertically installed is for sure the worst for most of the locations. As you can see here, for example, in Stockholm, I mean, that's a good example. For here in Kalama, you have big difference between a tilted module and a vertically installed module. But if you take now a look on Stockholm, due to the very north location, you clearly see that the difference between the 45 degrees tilted module, what is close to the optimum, to the 90 degrees to the vertically installed is very small, though even this shows local behavior depending on the sun position and how much sun hours you have per year. As last point, I want to go to the industry grid parity, because even grid parity, it's mentioned a lot in the PV. From my personal perspective, if you hear grid parity, it's not proper defined, because there are different level of grid parities. For sure, in most of the countries, the grid parity for private households or for residential is already achieved. If you take here a look on the industrial grid parity, here it's an example from the electricity price. I assume starting from roughly 9 cents, going slightly up over the years, and then the levelized cost of energy for Italy and Munich, and then you can see here when are the expected break-even points. That means that the system costs are on a level and the model efficiency is on a level so that you can produce energy below the grid parity, in this case the industrial grid parity, to have advantages for this kind of customers. Here on the right hand side you have a summary about the electricity prices for different countries, and on the next slide I will use for example Chile and Sweden for different kind of applications. So if you take now a look on Chile, if you have a 10 megawatt plant, and then if you have a self-consumption rate of for example 30%, and the electricity price, that means electricity price, what you need to pay if you consume from the grid, or what you save because you consume it by your own, will be here displayed as earning, because you don't use it from the grid. That means you save the 10 cents, what you can then use to pay off your plant. So in the first case in Chile, with the 10 megawatt plant and a yearly energy production of as an energy yield of 2,440 kilowatt hours per kilowatt peak, so in this case it's a non-tracked system, and a self-consumption rate of 30%, with the same with 10 cent electricity price, and then for the overcapacity, what you cannot consume, you sell it directly to the grid, for example here with 5 cents. Then you have a payback time of approximately 7.9 years. If you now increase the self-consumption rate, because we have a different customer and the self-consumption rate is 70%, with the same electricity price and the same selling price, you will directly reduce the payback time from 7.9 years to 5.8. That means for your customer, which have basically the advantages by reducing the energy bill, it's very important to have a high self-consumption ratio. A high self-consumption ratio can be only achieved if you really know the load profile from the customer, that you can analyze it and say, okay, we have a different kind of system, portfolio which we can offer, and this is the best option. A third point, because we say, okay, we don't have a constant electricity price. I made for Chile the same one with 7 cents and then only 30%. And then you can see if the electricity price is lower, for sure the payback time will be slightly higher. If you now take a look on Sweden with a residential project with a plant size of 10 kilowatt, and self-consumption rate between 30 and 70%, an electricity price of 23 US dollar cents, and even only a selling price of 5 cents, then you have payback times between 17.5 and 10 years. There you can see that for sure the location makes a difference, because the system price, okay, the system price for sure is different as well, depending on for example, on the material costs, labor costs. But I also can see that harvesting the energy yield here, what you can see here between Stockholm and Kalmar is approximately 2.5 times more in Kalmar, is impacting your payback time, as well as, for example, self-consumption rate, or for example how your system design looks. In this case, I'm already finished, so I will now check for questions. I will answering your question. If you have further questions after the webinar, you're welcome to write me an email. My email address is stefan.ringbeck@trinasolar.com. After the webinar, We will save the recording and the presentation, and we will distribute them to you. Okay, the first question, EW, it was always, it was asked what the EW is always for east-west. Another question is how soiling can be reduced. So for example, soiling can be reduced by better self-cleaning effect. That means that you have a different tilt angle, or if you, for example, use a frameless design, especially in locations where you don't have extreme soil accumulation like in Central Europe. Where basically the dust is more like then collecting, then the rain will wash it down, and then you have the soil increase starting from the frame, and with the frameless, this effect will be way reduced. Okay, that's it. So I answered all the questions. As said, if you have more questions, please send us an email, send me an email, and then I will answer them. Thank you very much, and we want to welcome you for our next session. Thank you very much. And if you want also to visit us at the Intersolar, then you also can visit us in Munich on the Intersolar, and then we can also discuss on the topics. Thank you very much. Have a nice day. Goodbye.